comprising of L1, L2, and C. The capacitor, right, included a fixed capacitor and a varactor, right. The varactor will change its capacitance according to the message signal. That's how we have seen, like VCO. And further, we have seen to get more stable oscillation, right? To get more stable oscillation, we have seen one scheme. And further, what we have seen is this direct method can be used to generate narrowband FM, right? If you have to generate wideband FM, we'll have to, right, go for some stages of frequency multipliers and mixers, all those aspects you have seen, right? So in today's session, we'll discuss about FM demodulation, right? So this is actually what a practical approach of FM demodulation, right? So an FM signal can be demodulated by using a simple differentiator and an envelope detector. We'll see how using a very simple differentiator and envelope detector you can demodulate an FM signal, right? So same circuit for FM demodulation or FSK demodulation you will use in your next semester, right? So in ADCOM lab you will right, do practicals on this, right? So but now we'll see how we can demodulate an FM wave using a simple differentiator and envelope detector. So topic is using differentiator and envelope detector. Envelope detector we have already learned, right? We have already seen envelope detector. So that is used to say detect AM signal, right? So in AM, the information was lying within the envelope of the modulated carrier, right? So by using a diode followed by a low pass filter, right, we were able to demodulate an AM signal, right? So we can use that in demodulating FM signal also, but before using that we should use a differentiator. So before this, maybe it has been quite a long since we actually studied the basics of FM. So in FM modulation, general FM modulation, if M of t is the message signal, and C of t equal to say AC cos 2 pi FCT was the carrier signal, right? So what happens is instantaneous frequency of the message signal will vary according to FC plus KF into M of t, right? So this is what is happening in frequency modulation, right? Instantaneous frequency of the message of the modulated signal will vary as a function of M of t, right? So FC is carrier frequency and M of t is the message signal, and KF, can anyone tell me what is this KF? It is frequency sensitivity. KF is frequency sensitivity, right? And right, we can write frequency deviation, right? Frequency deviation, maybe you can call it actually what delta, right? Delta can be, we have seen delta only for the case of single tone modulation, right? Where this M of t was AC cos 2 pi AM cos 2 pi FMT, right? Then there we have told frequency deviation delta is equal to what? KF into AM, right? There we have seen. But in this case, what will be frequency deviation? Frequency deviation is nothing but what? Maximum deviation in frequency, right, with respect to FC, right? From FC, what is the maximum deviation in frequency this modulated signal can have? That is actually what frequency deviation, and that is nothing but what? Maximum of, right, that is maximum of mode of KF into M of t, right? So this kf you can take out. You can also write kf into, right, this will be equal to kf into maximum magnitude of m of t, right? So this concept we have used in AM. We solved a problem, right, in AM, if you remember, right? There, right, modulation index, right, we have defined like this. So here actually what frequency deviation, that is maximum deviation in frequency with respect to FC, that can be defined like this. You can keep this in mind, right? So as m of t, we don't know what exactly is m of t, right? So we have seen delta only for a single tone modulation case, when we actually what referred a single tone modulation and we studied narrow band FM and wide band FM. That's how we proceeded, right? This general case of m of t we have not considered, but now, right, I'm going to introduce you to a demodulation scheme which is applicable to any, right, FM modulated signal, whatever be the message signal. It need not always be actually what a single tone modulated signal, right? So that is what we are going to study now, right? So I think this part is clear. Instantaneous frequency is equal to fc plus kf into m of t. So what will be instantaneous phase? Theta I of t. This will be equal to what? I have to. So what was the relation between instantaneous frequency and phase? Right. What was the relation? Can anyone tell me? You can type it in chat window. Right. The relation between frequency and phase. Right. So, or we know frequency, it is equal to 1 by 2 pi, right, d by dt of theta I of t, right? 1 by 2 pi times time rate of change of phase. That is how frequency is defined. So from this, you can write theta I of t. This is equal to 2 pi times integral 0 to t. Say I can write fi of tau d tau, right? So 2 pi times integral 0 to t fi of tau d tau. So this is how we can find out, right? So we can find out the instantaneous frequency, right? So in this case, what will be instantaneous frequency? So it is 2 pi times, right? I can write 2 pi times what is integral fc dt? That will be fct itself plus 2 pi times, right, 2 pi times kf into integral 0 to t m of tau d tau, right? So this will be the instantaneous phase of we have studied this already in the initial classes itself, right? So we are just recollecting it. These results we need, right? So any doubt in these things, please feel free to ask, right? Any doubt, right? If you are not comfortable with these things, what I have told now, you won't be able to appreciate the remaining part which we are going to discuss. So I would like to know if any doubt is there, right? Please type yes or no. At least some responses would be right. No one is asking anything. I think all are feeling sleepy after a nice meal. Right. So Sherwin have typed clear. Okay. So may now ask someone else also, right? So nothing is there, right? It's very simple, right? No doubt. Okay, fine. So CRs, right? Class representatives, you have represented your class, right? No, and okay. Once again, I will tell, if you have any doubt, please feel free to ask. Just type it in chat window, right? There will be many inhibition, right? May now like no any one of the reason, like okay, maybe now I'm not asking anything, right? So once again I'm telling, if you have any doubt, please feel free to ask. So I have to assume, right, all are clear with this aspects. So this theta I of t is 2 pi fct plus 2 pi kf into m of tau d tau, right? So now we can write what is the right FM signal, a general FM signal, right, or SFM of t. S of t can be written as AC cos, right? So what is the time domain expression of general FM signal, right? Now that you have told, you don't have any doubt, right? So can anyone type in here in chat window, the time domain expression for a general FM signal, right? Please, all of you, please do type it in chat window. It is AC cos of something. What is that something, right? Yeah, please do type in fast. Right, same thing, right? So if I ask some question, right, that will be for your attendance, right? I'll use the chat transcript to see the name of people who have typed in answers, right? So please do type in fast. Yes, very smart answer by Samar. It is theta I of t, right? Pratisha has typed 2 pi fct into m of t. That is not correct. It is or AC cos 2 pi, AC cos of, we have just defined theta I of t here, right? Theta I of t is there, right? This theta I of t is a, say, s of t. So AC cos theta I of t will be a FM modulated signal, right? So that is AC cos, sorry, cos 2 pi fct plus 2 pi kf into integral 0 to t m of tau d tau, right? So this is a FM signal, right? Now I told how it can be demodulated, right? So just now I told the steps, right? So this s of t, right? If you pass it through a differentiator, right? That is d by dt, right? Differentiator, right? Followed by an envelope detector. Envelope detector, right? So please excuse me, I will not discuss envelope detector in detail here, right? Because we have already discussed in previous module, and that video is available. So if anyone is having any doubt regarding envelope detector, you can either ask me or else you can refer to those videos. So we'll get demodulated signal. So I have to give s of t here, right? We will get demodulated signal or m of t, not only m of t, say m of t with some multiplication factor. That's what we will get here. We'll see what exactly we will get here, right? So this envelope detector in turn is actually what it has a clipper or a clipper followed by a low pass filter, right, which will clip off the positive part or negative part of the wave and it will be passed through a low pass filter, right? So now let us just see what will happen, right, if you pass this s of t through a differentiator, right? So here what we'll get, here we'll get d by dt of s of t, right? So we'll find out what is the output here, right? That is d by dt of s of t. It is equal to d by dt of AC cos 2 pi fct plus 2 pi kf integral 0 to t m of tau d tau, right? So what is this derivative, right? So it is d by dt of AC cos something. What is derivative of cosine? D by dt of cos, it is plus sign or minus sign, right? What is it? Pratisha, you have typed general. I didn't get. What is that?
That equation, sir.
2 pi fct into m of t.
The S of t general equation.
S of t general equation. Okay, yeah, fine. So okay. Now my question is whether derivative of cosine is plus sign or minus sign. So I got two answer. It is minus, right? Okay, it is minus sign. So I'll go forward with minus, right? So we will get minus AC, right? Sine 2 pi fct plus 2 pi times kf times integral 0 to t m of tau d tau, right, times, right, then what I should do, this is sine of some function of time, cosine of some function of time, right, will be, derivative of that will be sine of whatever be the argument multiplied by, right, derivative of this, whatever they're inside the bracket, derivative of 2 pi fct plus 2 pi kf times integral 0 to t m of tau d tau, right. So this will be the derivative, right. So derivative differentiator, right, differentiator is nothing but what it is, a say a filter, right. Differentiator can be, differentiator is a linear time invariant system, right, can be implemented as a filter, right. So maybe you can try out this in multisim or something. I can give you the circuit, right, the same circuit which you will be what using in higher semester for FSK demodulation, right. Even though FSK is a digital modulation technique, for FSK demodulation also we'll be using same thing. I can give you the circuit, you can just try it out in multisim if you want, right. So what you have to keep in mind is this differentiator, right, it is a right, it is a linear time invariant operation, right, that you have to keep in mind, right, and that can be implemented as a filter, right. So okay, so this is equal to again minus AC sine 2 pi fct plus 2 pi kf into integral say 0 to t m of tau d tau, right, this into, right, d by dt of 2 pi fct is nothing but what, 2 pi fc plus what is d by dt of 2 pi kf into integral 0 to tau, so it will be 2 pi kf times what is d by dt of integral 0 to t m of tau d tau. What is this? Can anyone tell me? What is derivative of integral? What is that? What is derivative of integral? My question is, what is d by dt of integral 0 to t m of tau d tau? Right. What is that? No answer. Right. It's surprising. It's a very simple question. Right. Yeah, it's m of t itself. Right. You are taking derivative of integral. Right. So it will be m of t itself. Okay. Thank you, Sherwin. Right. So 2 pi kf into m of t. Right. So why I got this? So this, right, integral derivative of integral will be equal to what? That function itself. Please do remember this. Right. So because of this, right, we are getting this, right. Now what I can do is I can just rearrange it slightly so that, right, it will look like an AM signal. So I'll take all the envelope part, right. So what do you mean by envelope of a sinusoid? Envelope of a sinusoid is nothing but what, it's amplitude part, right, it's amplitude part, that is the envelope, right. So now I'll just take all the envelope, so minus AC, right, then 2 pi fc plus, sorry, plus 2 pi kf into m of t times sine 2 pi fct, 2 pi fct. Please note it down along with me, right? You have plenty of time, so please do take it down along with me, right? 2 pi kf times integral 0 to t m of t, m of tau d tau, I'll write m of tau d tau, right? So this is a sinusoid, right? This is a sinusoid, and this is the envelope part, right? This is the envelope of a sinusoid. Envelope of a sinusoid is nothing but what? The amplitude, right? So in this case, amplitude is actually what? It's not a constant. Amplitude in turn is actually what? A function of time, right? Amplitude in turn is a function of time. So if you pass this through an envelope, now I'll go back to the say, or else I can draw it again. That would be better rather than going up, right? So initially S of t is passed through a differentiator, right? S of t is passed through a differentiator, right? After it is passed through a differentiator, this is what we are getting, right? D by dt of S of t is what we are getting here, right? Now, right, we have to pass it through an envelope detector. Right, we have to pass it through an envelope detector, right? So this signal is what is passed through an envelope detector. So if it is passed through an envelope detector, what we'll get? We'll get the envelope, right? Envelope, what we'll get is this, right? Minus AC 2 pi say FC 2 pi KF into M of t. This is what we'll get, right? So what we'll get here is say minus AC 2 pi FC plus 2 pi Kf into M of t, right? Now what we'll do is we'll just, right, you remember for this envelope detector to work, right, for this envelope detector to work, right, the modulated signal should satisfy certain conditions, right? We have used envelope detector to demodulate standard AM, right? And we have seen if standard AM has a phase reversal, right, as a phase reversal, right, then we can't use envelope detector. Why? Because if there is a phase reversal, the information will be what residing both in positive and negative envelope, right? So but when we pass a signal through an envelope detector, we'll get either positive or negative envelope, right? So modulated signal with phase reversal, when it is passed through an envelope detector, it will give some distortion, right? So for this demodulation scheme to work, right, so this particular, you can see this as actually what an AM signal. You can see this as an AM signal, right? So this AM signal should not have any right phase reversal, right? I'm just telling you to see it as an AM. It's not exactly an AM signal, but right. What we can do is we will just try and find out what is the condition for not to have phase reversal, right? So this is the envelope what we'll get, right? This is the envelope what we'll get. But if you have to get this envelope as such, what should happen is there should not be any phase reversal, right? So then we'll try and find out what is the condition for no phase reversal, right? So for that, we'll just rearrange the envelopers, right? AC, that minus sign I'm not considering, for instance, AC 2 pi FC plus 2 pi KF into M of t, right? This is the envelope. Anyone remember what was the time domain expression for standard AM? Right? Anybody remember that? Time domain expression for standard AM, maybe I'll write it here, right? S AM of t, the time domain expression was AC into 1 plus Ka times M of t cos 2 pi FC t, right? Where this part is our envelope, right? This is our envelope, and this is actually what our sinusoid, right? This is our envelope. So here our envelope is this. So if we can rewrite this envelope in this form, then we can tell what is the condition for not to have phase distortion, right? Phase reversal. So in this, what was the condition for no phase distortion? In this case, the condition for no phase distortion was, right, this Ka into mode of M of t, right? Ka into mode of M of t, that is max of this. Maximum of K into mode of M of t should be less than or equal to 1, right? So this was the condition for no distortion, right? No distortion or no phase reversal, right? No condition for no distortion or no phase reversal was this, right? So now can we rewrite it like that? Something like that? Can we rewrite it? Right. So we, of course, we can rewrite it. If you take this 2 pi FC common out, first term will become 1, and whatever remaining, right, we'll have right. So we can do that. So this is equal to, right, AC 2 pi FC, right, AC 2 pi FC times 1 plus, so if you, right, so it will be 2 pi kf into m of t divided by 2 pi fc. So 2 pi and 2 pi will get cancelled, so we'll get kf divided by fc times m of t, right. So this entire thing AC times 2 pi fct, right, this is corresponding to what, AC in our standard AM signal, right. This one is there as such, right, one is there, one is here. Then instead of Ka, we have actually what, Kf by Fc. Kf by Fc will be actually, maybe we can call it as, we can see it as amplitude sensitivity of this particular signal, which can be compared to AM, right? So why I am doing this, we should know what is the condition for no phase reversal, right? No phase reversal, no phase reversal, right? So in this case, so now what is the condition for no phase reversal? So I'll write for no phase reversal. For no phase reversal, right? The condition is, right, say 1 should be greater than or equal to Kf by Fc times max of m of t, right? 1 should be greater than or equal to Kf by Fc times max of m of t, or else I can write Fc should be greater than or equal to, right, Kf times max of m of t, right. Fc should be greater than or equal to kf times max of m of t. Do you know what actually is this kf times max of m of t? We have seen it before, I have told, right, we have discussed it just before. If you move up, right, I'll just show you, right, we have written kf times max of m of t somewhere, right, when we discussed about, yeah, right. So this kf times max of m of t is nothing but what, the frequency deviation. It is the frequency deviation, right, delta. Kf times max of m of t is nothing but frequency deviation or delta, right. So right, yeah, so the condition for this modulator, right, condition for this to work is, right, so kindly excuse me, right. Yeah, sorry, right. So we are back. So now the condition is, condition for no phase reversal, or we'll be able to use this particular demodulation scheme, right? We'll be able to use this particular demodulation scheme for FM only if this condition is satisfied. What is the condition? Right. The condition is FC carrier frequency should be greater than or equal to frequency deviation. Frequency deviation. Right. So normally in general FM cases, right, this condition is easily satisfiable, right? So we'll just see an example, right? An example. Maybe we'll take the case of this FM radio, right? We'll take the case of FM radio, right? Can anyone tell me what is the frequency range used for FM radio? Right, we have discussed it long back, maybe in the first class itself, right? So what was the frequency range used in FM radio? Yeah, you can type it in chat window. Right, you can type it in chat window. The range of frequency, right? Whether it is say 10 kilohertz, 100 kilohertz, 88 to 108 megahertz. Okay, excellent, Pratisha. Thank you. Right. So it is 88 to 108 megahertz. Maybe I'll take as a 100 megahertz as actually what a typical carrier frequency, right? For us to do a calculation, right? Let right FC is equal to 100 megahertz, right? Let FC is equal to 100 megahertz, and our message signal is actually what? Our message signal is our voice signal, right? Message signal is voice signal or so audio signal, right? It will have say frequency content from 300 hertz to say some 15 kilohertz, right? So this is our message signal and its spectrum M of F, right? Audio signal. The maximum frequency so I can consider this as actually what FM or W, that is equal to 15 kilohertz, right? That is equal to 15 kilohertz. And let us also assume the modulation index beta to be equal to say 10, right? Let us also assume modulation index beta to be equal to 10. In that case, we'll see what is the frequency deviation in this case, right? So yeah, okay. So yeah, so FC is equal to 100 megahertz and say FM is equal to say 15 kilohertz, right? And what was this frequency deviation delta? Delta we have studied, it is equal to or else yeah, beta is equal to frequency deviation divided by FM, right? Right, this is frequency deviation, right? Beta is frequency deviation divided by FM. So which implies here 10 is equal to delta divided by 15k, which implies what will be delta in this case? Which implies delta is equal to 10 into 15k. It is equal to what? 150k, right? 150k in terms of megahertz, it is 0.15 megahertz, right? Is it correct what I've told? What I've written? Right, delta is 0.15 megahertz, right? So this is the maximum frequency deviation, right, which can happen in an FM transmission. What does that mean? If you are using a center frequency, if you are using a carrier frequency equal to 100 megahertz, the FM modulated signal will have frequency 100 plus or minus 0.15 megahertz, right? The maximum frequency content will be 100.15 megahertz. Minimum frequency content will be 100. Sorry, say 99.85 megahertz, right? So our condition is FC should be greater than or equal to delta. That condition is easily satisfied here. Right, that condition is easily satisfied, right? So for almost all practical say FM signals, we can use this differentiator followed by envelope detector, and also we do have actually what indirect and direct methods that actually what Prasad sir will be teaching you in through this video, right? So that methods are also there, but this is the most common and general and easiest method for demodulation, right? But the problem is, if you see the output, right? Output, the envelope is, right? This is the envelope what we are getting, right? This is envelope what we are getting, right? So maybe you should pass this through a filter or attenuator, right? Or a filter with right gain equal to 1 by this, right? So that you will get 1 plus kf by fc times m of t, right? So from this, practically, if you have to get m of t back, what you should do is you should pass this through a I'm just telling it, right? So if you should pass this through a block with gain 1 by AC 2 pi FC, right? Then you should, right, clamp it, right? So 1 plus means you are adding a DC value. It's actually what? Clamping a signal up, right? It's like clamping a signal up, adding a DC value. So if it is sine 2 pi FCT, it will be, right, varying with respect to 0 voltage, right? And if it is 1 plus sine 2 pi FCT, what will happen? Its DC level is shifted up. So that wave will be shifted up by 1 volt, right? So then you will have to clamp it down, right? You will have to clamp it down by say 1 volt, right? Then what you should do is, again we have a gain kf by fc times m of t. So then if you have to get exact m of t back, you should pass it through a filter again with gain fc by kf, right? So maybe you have to do these things. I mean to say, you'll have to do some sort of sorry, signal conditioning to get the original m of t back, right? But more or less we are interested in variation in amplitude, right? Information mostly will reside within actually what variation in amplitude, so that can easily be what identified from the signal itself, right? Only thing is actually it is DC shifted and a sort of magnified or attenuated, right? So this is how we can demodulate an FM signal, right? So maybe what I'll do is, as I have project review now, right, I'll end today's session here, right? Maybe I can spend some 3 to 4 minutes. If you have any doubt, you can just ask me, right? Is it clear what we have discussed? We have discussed a small topic, right? We have seen how a differentiator followed by an envelope detector can be used to say demodulate an FM signal, right? And what is the condition the FM modulation should satisfy so that we can use this signal, right? And we have even seen a very simple problem, right? An example, a real example, and we have showed that this constraint, right, FC should be greater than frequency deviation. That is easily satisfiable, right? So that is what we have seen. Any doubt in this? Yeah, if any doubt is there, please feel free to ask. If you have no doubt, please type a no. Right, it's neither. Whether you people were listening to the class or you were doing something else. Yeah, okay, fine. So I hope it's like I know these things are easy. You can study it even if it is the last moment, right? You people can learn and score, but right, yeah. So that's it for today. Maybe we'll wind up today's session here, right? And tomorrow, right? Do we have class? No. Okay, yeah. Somewhat given, yeah, no class. So maybe what we'll do is the next session, right? We'll continue with, right, maybe some aspects of PLL, right, and we'll just have a 15 to 20 minute discussion on whatever videos we'll be posting, right? Tomorrow, no class. So first hour, okay, fine, yeah. So that's it. Right, that's it for today. Right, we'll wind up.